Okay, welcome back. In this particular lecture, we are going to cover review the fundamentals of the first fundamentals of the zeroth law of thermodynamics, temperature, basis for calculating temperature, and we will discuss about pressure and some of the devices which are typically used to find out pressure or pressure differences. So, this is our learning objective. Okay, so let me just go through the zeroth law of thermodynamics. Obviously, you all have know this concept very well, but just to summarize. So, what we say about zeroth law of thermodynamics is that if two bodies are in thermal equilibrium with a third body, they are also in thermal equilibrium with each other. And in other words, you can replace the third body by a thermometer, and thus your zeroth law can be restated as two bodies are in a thermal equilibrium if both have the same temperature reading, even if they are not contact. Okay, so that has become basically the zeroth law of thermodynamics. Now, practically, it means that we need to understand how the thermometers work. Okay, now all the temperature scale which has been devised are based on some easily reproducible state. Okay, and this state is basically ice point and steam point. So, basically 0 degree and 100 degree. Okay. So, the point is that you can consider any particular fluid and you can scale it in such a way that you get 0 degree and 100 degree, but the point between 0 to 100, if not even if you calibrate only the 0 and 100, the other points may differ. The reason being that the thermal expansivity of the fluid vary from each other, and that is why such a thermometer are not commonly used. The one which is used is basically based on either ideal gas thermometer, which shows that it is independent of the gases which are considered, and the scale is linear as a function of temperature. In other words, the pressure is linear as a function of temperature. Okay, and thus you can change the gas and still you can achieve the same points, and you can still calibrate it well. Or the same thing which you can use in ideal gas thermometer is by considering absolute temperature scale, which is based on the second law of thermodynamics, and both are equivalent. It can be shown. So, in case of absolute thermodynamic scale or thermodynamic temperature scale, the examples are Kelvin and Rankine scale. Okay. Now, pressure, of course, pressure we all know it's a normal force per unit area. Is typically used for gas and liquid. We don't use the pressure for solid. We use stress, normal stress for solids, and the unit depending on the SI unit is this, other units are given here. Now, it is very clear that the pressure exerted or felt by the feet of a chubby person is substantially larger than that for a slim person. Okay. Now, what is the variation of pressure? Now, pressure of a fluid at rest does not change in the horizontal direction. Okay, so that means there is no once it is at rest, because there is no flow, so the forces along the horizontal directions are going to be constant. Okay, so this pressure and this pressure, if at rest, is going to be same. Okay. Now, let us consider a rectangular region which is this. Okay, and I do a simple force balance for this particular mass within the rectangular element. So, the force balance should be, because it is not flowing, should be 0. So, which means this is basically the force acting on it, okay, on this from below. This is the force due to the air, okay, or due to the fluid above it acting on this particular element, and this is basically the mass or the weight of not mass, this is the weight multiplied by, or rho g multiplied by the volume, which is nothing but the weight. So, if you do a simple mathematical calculation and take it out the common term, what you get is nothing but that P2 minus P1 is nothing but minus rho g delta H. In other words, P below is more than P above by this value. Okay. So, the pressure increases linearly with distance as we go down in depth because of the added weight of the fluid. This also tells you that the pressure along the horizontal points for a given fluid will remain constant, though the pressure in depth increases, but this complex geometry tells you that the pressure here same as here, 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 here and here, and pressure here and this are not same for simple reason is this is a different fluid. Okay, so you need to have the same fluid in order to have the equality of the pressure. Okay. Now, what are the measurement devices for pressure? One is the simplest one is a barometer, which is used for atmospheric pressure. Okay. So, for example, this is a simple device. Due to the vacuum, the pressure here is this. You can apply a force balance and you can show that P atmosphere is nothing but the density of the fluid which you consider, which is nothing but the mercury, the G gravity and the height which is being which it rise due to the pressure, and for 1 atmosphere this is nothing but 760 millimeter Hg. Okay. Now, it also tells you that the cross sectional area of the tube has no effect on the height of the barometer, and even though you use a different column the height will remain the same. Okay, because of the simple balance here. So, in addition to barometer, we have also other devices. For example, if you are interested in measuring the pressure of a container having a gas, one can use a fluid column to measure simple pressure difference, and that can be used to measure the pressure of the gas container. Okay, this fluid could be any fluid, mercury, water, alcohol or oil. So, this is an example here. For example, if you are interested to find out the pressure of this gas, since gas is typically have very small density compared to the heavier fluid. So, pressure here would be same as pressure at P1. Okay. Now, P1 pressure, because of the force balance, this is not moving, the P1 pressure here in this side and this side should be same because of the force balance. So, P1 and P2 should be same. So, and here is a P atmosphere. Okay. So, now you can simply use P2 is equal to P atmosphere, okay, plus the rho GH. Okay. So, this is a simple way to calculate. So, that means if you calculate P2, you know exactly what is P1, and that means the gas of the container. Now, in addition to this, you have manometer, which many times you stack up the fluid layers, and in this case you have 3 fluids having these heights, and one can relate P pressure at 1 with respect to P atmosphere and the density of this fluid with different heights. So, one can simply use P atmosphere plus the rho 1 G H1 plus rho 2 G S2 plus rho 3 G S3, and this is exactly what has been done to achieve P1. Okay. One can also use differential manometer in order to find the pressure difference between 1 and 2. So, we can start from P1, okay, and go down in the height. It does not matter what kind of geometry we are using. What we are interested is it should be of same fluid and effectively the height of the from this point to whatever, for example, this point. So, P1 is this plus rho 1, which is the fluid here, which we are interested to find the difference from these 2 points. So, rho 1 G plus whatever the height from this point till A, which is nothing but A plus H, and that is what you get, rho 1 G A plus H. Now, this PA is same as whatever is at PB. So, we do not we go from here to directly to here, and now we are going up in the direction. Okay. So, we are going to subtract the rho GH from this term. So, that will be rho 2, because this is rho 2 GH here. Now, from here to here we are going to subtract minus rho 1 GA, and thus we are going to find out the pressure at 2. So, if you readjust this term, we get P1 minus P2 is equal to rho 2 minus rho 1 GH. So, that means the pressure drop from here to here is equal to the difference in the density of this fluid of this with respect to rho 2. So, rho 2 minus rho 1. So, rho 2 is usually is going to be much larger than rho 1. Okay. So, now we can do a simple example here to exercise this, a piece of experimental apparatus as shown in the figure below, okay, is located where G is 9.5 meter per second square and the temperature is 5 degrees Celsius. Airflow inside the apparatus is determined by measuring the pressure drop across an orifice, which is nothing but this, okay, with a mercury manometer, okay, and the density is given, showing a height difference of, so this height is 200 millimeter, okay. So what is the pressure drop from, okay, across the orifice? So in the word, what is the pressure drop, let us say from here to here, and the pressure drop from 1 to 2 can be written as simply here. Why? Because of course the density of the air is extremely small and this height difference will not bother. The density of the air is close to 1.2 kg per meter cube. Okay, so now we have done this exercise before, that the pressure P1 minus P2 is nothing but rho 2 minus rho 1 GH. So, okay, rho 2 is of course the density of the mercury, rho 1 is density of the air. Now, this we can ignore also because 13,600 minus 1.2 is going to be negligible. So, for engineering approximation we can simply write rho HGH and this comes out to be this value. Okay. Okay, so here we ignored rho 1 and simply written rho GH HG and that is what the value is. Okay. So, so that will be the end of this lecture. So, where we discuss very quickly the temperature concept and as well as the pressure. Okay. So, we will see you next time where we are going to introduce rather review the energy conservation in the first law of thermodynamics.